Hello everyone, welcome to the session 2 of week 2. We will talk about direct energy deposition DED, sheet lamination and a few hybrid and newer technologies. We will go into the first principles of direct energy deposition, learn how sheet lamination is done and what are the value additions, and some of the newer technologies that have come, not only in the heavy engineering applications but some other fields also, for example biomedical. We have learnt now many 3D printing technologies that have been recognized by ASTM. Today we will talk about direct energy deposition, and just to remind you, the ones which are shown with blue rectangles are available at Wipro 3D and they are used on regular basis. In direct energy deposition, the energy source is focused onto the workpiece. The metal wire or powder, they are coaxial with the laser beam and they are introduced at the focus of the beam, and that makes the feedstock melted before it is deposited on the build platform or on the substrate, and once that is done on subsequent layers as well, the same process is followed. An inert gas is also supplied so that the energy source and the feedstock both are protected, and thus we can avoid the formation of oxides or any other unwanted contamination. A schematic of DED process is shown on the bottom right corner. There are 4 major elements here. One is laser source. We have laser optics to control the laser. We have powder or wire feedstock, in this case powder, that is being fed and it is coaxial with the laser beam. And we have a shielding gas which is protecting the laser source and also the feedstock throughout its way before it is deposited on the substrate, right. And as you can see that the formation is a layered structure and thus large parts can be formed because this all assembly can move to various locations. Thus there are many advantages of this process. We have very high deposition rates because we can have multiple wires depending upon what is the power of the source. We can also have larger amounts of powders and thicker wires possible. Thus we can also build large volumes. The setup is cheaper because we do not need a chamber or creation of vacuum for this, and no supports are required like in many other 3D printing technologies. However, this technology also comes with certain limitations. We have poor quality of surface, as you can see that as the layers are deposited, the side surfaces are very rough and you can clearly see the formation of multiple layers. Thus the surface has to be machined. Even the top surface shows the formation of various build paths, and that surface also needs to be cleaned. Thus post processing is required. We can deposit only the metals that can be welded using DED process. There are many machine manufacturers for DED deposition process. There is Beam, we have Trump F, we have Norsk Titanium, and Optomec, we have BAM Incorporated, we have Siaki Incorporated, and DMG More Additive. Like mentioned earlier, titanium alloys, aluminum alloys, Inconel, various types of Inconel, various types of steels, tungsten and niobium alloys can be deposited. This technology is also used for various repairs process. For example, if there are any damages to large structures like a bridge, those repairs can be done using the DD process, since the assembly is not very large and it can be transported wherever the repair is needed. It can also be used for repair of smaller structures like turbine blades. It can also be used for making the turbine blades from scratch, like the other technologies are used. And since it is a faster technology, the overall throughput using DED is much faster. It can also be used for making large complicated structures, because the degrees of freedom available using DED are many more. Thus, hollow cylinders or pressure vessels can also be made using this. Depending upon the raw material that is used or the energy source that is used, the DED process can be classified into many types. Whether a powder feed is used or wire is used, it can be a powder DED or a wire DED. Depending upon the type of energy source, it can be a laser or electron beam or plasma or kinetic energy DED. The first three are very intuitive to understand. In the last one, the kinetic energy DED, high velocity small particles are shot on the substrate, and because of this high kinetic energy in smaller size, they get deposited because the kinetic energy converts to the heat energy. Now we will talk about sheet lamination. The object, which is sheet, is drawn across a build platform, and that drawing process is done using a set of feed rollers or pulling rollers. There is a arrangement which can also cause heating of the roller, and ultrasonic waves can also be used through the same roller, so that using ultrasonic heating the alternate sheets can be joined, and this roller passes over the sheets to cause additive manufacturing. Sometimes some additives can also be added between two sheets. A schematic of sheet lamination process is shown on the bottom right. There are four major elements. One is a build plate. We have the feedstock sheet, which is in this case being pulled from left to right. There is a roller which passes over alternate sheets. For example, if you have put a sheet already, you can pass the sheet on top of the existing one or on top of the substrate. The roller will pass over it, will apply some pressure and also heat and ultrasonic waves if needed, and will cause joining. Finally, using a laser source, which is item number 4, the desired shape can be cut out from this multi-layered structure. There are some advantages of this process. One, as you have already seen, is that it requires no support structure. There is no chemical reaction. We are just doing joining using temperature or using ultrasonic waves, or maybe some additives in case of polymers. It is a low cost process because no specially designed chamber is being used, no vacuum is being used, and even this facility can be transported fairly easily. However, there are some limitations. As you have seen that the primary structure that is being created is a cuboid shape. If you need to create a more complicated geometry, we need to apply laser, and the creation of hollow items is quite challenging. We will have to machine, if needed, the hollow item from this cuboid shape, which is quite cumbersome. There are some manufacturers, one is Clean Green 3D and the other is Fabrisonics. There are many more, we have listed only these few. Aluminum alloys, copper alloys, various stainless steels, titanium alloys have already been tried with this process. In addition to that, even materials like carbon fiber composites can be printed very easily, and various metals, as you have seen here, can be printed, and if complicated shapes need to be printed or need to be formed, layered structures can be formed first and they can be shaped into the desired geometry as shown here. Apart from the sheet lamination and DED or various PBF methods or lithography, there are some newer techniques that have recently come, and there are many innovators that have applied those newer technologies for fields other than classical engineering. For example, Triestech has come up with a proprietary technology which is called melt extrusion deposition, using which they are creating programmed tablets for drug delivery, and we will talk about it in a bit detail in upcoming slides. The other technologies that have been introduced by Triestech are semi-solid extrusion, micro injection molding and micro droplet jetting, and these names are very intuitive because as the state of the material which is being extruded, depending upon how much is the content of the liquid in that, the technology can be called either solid or semi-solid and so on. Company called Fortify have introduced a process called digital composite manufacturing, where a resin with the presence of fibers which can be magnetically aligned is used for making RF source, which are radio frequency source, and various dielectric shapes which can be used for applications in space and satellites. In RF applications, the field of RF depends on what is the texture of the surface and what are the geometries in which RF is being applied. Another company called Alloy Enterprises has come up with technology which is fairly well known as diffusion bonding to create larger structures, where the aluminum plates are put on top of each other like this, and some amount of heat and pressure are applied, and after leaving them for some time, the joining happens at the interfaces. Using this technology, depending upon the area on which the operation is going on, larger volumes and structures can also be created. Essentially, as you can see, this technology does not need any powder. We can start working with the feedstock which is in form of sheets. Depending upon also the source of pressure or the heat, the thickness of these sheets can be decided. Another company called Phonotech has come up with a 3D printing technology which can be used for microelectronics parts printing. What they essentially do is they create grooves on boards on which the circuits have to be printed. For example, like this, these grooves are filled with the material using which the circuit has to be made. Let us assume it is copper. and then all of the material all over the board is fused using a very high flux of heat, and thus the printing happens in one go all over the board. So, it is a very efficient process for printing electronic boards. A company called Seoret Technologies has come up with a novel laser powder bed process, which is very innovative in the sense that instead of printing small parts of a large object, whole area can be printed using lasers, and we will talk about it in detail. A company called Melt Technologies is using additive friction stir technology for creating large blanks of legacy parts which are difficult to make using classical processes such as castings and forgings. Let us look at some of these hybrid and novel technologies in detail. Let us take a look at the friction stir deposition process, which is being used by Melt Technology for printing or additive manufacturing of large blanks. In this process, there is a melt tool which rotates on top of a substrate. The feedstock is fed through the rotating tool only. Because of the friction, lot of heat is generated and the feedstock material goes through severe plastic deformation. Because of the severe plastic deformation and heat, the feedstock gets deposited on top of the substrate, and if this process is repeated, we can create another layer of the feedstock on top of it, and thus additive manufacturing is done. A real picture of a part created using friction stir deposition is shown on the right. As you can see, there are multiple layers of the raw material or the deposited material in this case, and the surface roughness is not very good, which calls for the need of some post processing or surface finish. Overall, here are some takeaways. In the literature, it is reported that very large structures, for example 20 feet by 20 feet by 20 feet, can be created using this process. Any metals, even refractory metals like niobium, can be printed. As you can see, no chamber is required, and thus the cost of the process is not very high. There is fast rate of deposition because it depends only on the feedstock that we are using. The final property, as you can intuitively see, can be as good as that of a forged structure because the feedstock is going through a severe plastic deformation. Depending upon whether the feedstock is in pure form or some additional particles or fibers are also being added, metal matrix composites or similar composites can also be created. The new technology that we mentioned earlier, similar to laser powder bed fusion developed by Seoret Technology, is discussed here. In this method, a laser beam is split into many small pixelated lasers, and instead of printing along a beam path within a single structure, the printing actually happens in form of tiles. Since the overall beam is split into many smaller beams, the whole area wherever that set of beams is focused can be printed. Essentially, it works like display on a television screen, where the whole screen is divided into millions of pixels, and an area of the build platform is illuminated using the laser, and wherever that area is, the powder in that area gets fused with the underneath layer. Thus, very large parts can be created in this tiled manner. The process essentially works like a micro welding process. Instead of the whole powder particle being fused, it only is welded with the layer which is underneath it. And as you can see, the printing essentially does not happen along the whole laser beam spot, but it happens along the millions of smaller laser beams which have been split out of the initial laser beam. Since the pixel size of those smaller laser beams is very small, it can be as small as 6 to 10 micron, there is less interaction of the laser with the material, and thus a much better surface finish can be achieved. Overall, the important takeaways are that the laser beam is split into millions of smaller laser beams where micro welding is performed. Large areas can be printed because it is printing of area and not because of the beam. The surface roughness is good, particularly because the interaction volume of smaller laser beams which have been split is much smaller. As mentioned earlier, Tri-Stack technology has come up with an innovative 3D printing technique for making drugs. Using this method, tablets or drugs can be printed with multiple layers and virtues such that the tablet or the drug is delivered within stipulated time at the specified location. This technology can also be used for on-demand drug manufacturing based on the patient's need. So, individualization can be done. A very controlled drug delivery can be performed, and along with the printing of the drug or the other material, micro devices for imaging and tracking can also be embedded. An example for manufacturing or design of a colon targeted drug is shown here. This is a 3D printing technology where there are 3 layers. One is enteric layer, which is introduced for maintaining overall integrity of the core of the drug while the tablet is in the gastric acidic environment. In the second layer, we have another type of material which erodes slowly and at a prescribed constant rate while the drug or the tablet travels through the intestine till it reaches the target, which is colon in this case. By the time drug reaches the colon, the other 2 layers have eroded already, and only the core, which is the main drug, which needs to attack the specific areas of colon, reaches there, and it starts releasing various ingredients which are part of the core. As mentioned earlier, we can also introduce the tracking devices somewhere in the drug, maybe around the core area, or even imaging devices somewhere, so that the location and the condition of the tract and the colon can be figured out. Each layer in this drug can be manufactured using specific material so that the properties that we need in each layer can be controlled. Those properties can also be controlled using the speed of manufacturing or the type of slurry or the feedstock that is being used. For example, we can introduce a rough surface texture using specific process control, or even the raw material on the top surface. We can have a different type of slurry so that the erosion rate can be controlled, and the core of the tablet can be designed and deposited using altogether a different process and material. Thank you for listening